Hey guys, welcome back. So let's go ahead and get moving again and start talking about the rest of our lecture 5 topics. So we just got done with our review. Let's start yet again. The next thing I have for you is, who is this guy Avogadro? You may have heard of him. I always thought of him as Mr. Avocado, but he's a dude. Question. Just like we can say that a dozen is 12 of anything, we can define a mole as Avogadro's number of particles in one element or compound. Avogadro's number is 6.0221413 times 10 to the 23rd. We generally round this to 6.022 times 10 to the 23rd. One mole contains 6.0221413 times 10 to the 23rd atoms or molecules, depending on what we're talking about. Moles are so much easier to work with. So it's like talking about a dozen, but it's a huge number instead. Our molar mass, these numbers that we see on the periodic table. So when we deal with this number right here, 51.996 for chromium, that mass is defined as the mass that 6.0221413 times 10 to the 23rd atoms of chromium has. Okay, so it's defined as the mass of one mole of that atom. Mole of that atom is 6.0221413 times 10 to the 23rd atoms of chromium. So they're all equivalent to each other. So, otherwise, I'm so sorry. So, again, we can say one mole, 6.0221413 times 10 to the 23rd atoms equals the molar mass. And so if we're talking about chromium, it's 51.6 grams. Okay, so it's whatever we read from the periodic table. And usually we would list this as grams per mole. Okay. It could also be atomic mass units that we're talking about. So it's interchangeable there too. That's what we're dealing with. Cool? It's impossible. So the mass of one mole of a substance is the same as the atomic mass, provided you use the atomic mass on the periodic table. Those mass values take into account the normal distribution of the isotopes. So that mole should take into account that same distribution. And that means if I know the mass of a sample of an element, I can know the number of moles of that element that I have. That'll tell me how many particles are present. So let's look at an example. I have 13.56 grams of lead. What's the molar mass of lead? Okay, where is lead? Yeah, we gotta find lead. Where is lead? It's interesting. Where is lead? Well, lead is on this table somewhere. Where did lead go? Listen, here he is. Lead is Pb. So lead is one of those things the same for a word in another language. If I'm not mistaken, I think that's Latin. Lead is actually the material that used to be pipes were made of lead, and they were used by plumbers. So plumbers, PB, lead pipes used by plumbers. So there you go. All right. So there is a connection there. That's how I remember that it's PB. So lead is listed as 207.2 grams per mole. The molar mass of lead is 207.2 grams per mole. Okay. So if I have 13.56 grams of lead, that's the mass that I was given. I want to know how many moles is that? That's an interesting question. So if I have 13.56 grams, and I know that 207.2 grams of PB is 1 mole of PB. And I can cancel the grams, and that would convert me into moles. So I can take 13.56 divided by 207.2, and that gets me that gets me 0.0654440154 moles of PB. And then the question becomes, how many sig figs should that be? Now, this number right here, 207.2, is a conversion factor. So it is not considered one of the numbers that I should look at to determine how many sig figs I have. The 13.56 is what I consider. That is 4 sig figs. Therefore, my answer should be 4 sig figs. So 1, 2, 3, 4. 0.06544 PB is what I have. So 0.06544 moles of PB. Now, how many atoms is that? Okay. Well, that's an interesting question. Now I know how many moles I have. 0.06544 moles of PB. I also know, based on what we talked about before, that 1 mole of anything has 6.022 times 10 to the 23rd atoms in it. That's the conversion factor that we just introduced on the previous slide. So right over here, know that 1 mole contains this number. Now I have rounded it to use this number right here. Okay. But again, it's a conversion factor, so I don't care how many sig figs it has. So I take this number and I multiply those two things together. Now, am I going to use the rounded number that I calculated, the 0.06544, to do this calculation? Or should I use everything that it spit out on my calculator, i.e. this number right here? I should use the number that's still in my calculator, this number right here. And then I should multiply that by times 6.022 second EE23. And that would give me 3.94103861 times 10 to the 22nd atoms of PB. Okay. Looking at that, I'm still looking at 1, 2, 3, 4 sig figs. So this would be reported as 3.941 times 10 22nd atoms of PB. Okay. So that would be the number that I would report right here. 3.941 times 10 to the 22nd atoms of PB. So even though I may report a number that's been rounded, when I go to do the next calculation, I always work with the number before it's rounded. Okay, it is important that you do that. Does it always actually make a difference? That depends. So sometimes it will, sometimes it won't. Make sure that you always do it. Make sure it's your habit that you're building, because sometimes it matters and sometimes it doesn't. Alex will kill you points-wise because it will tell you that it's the wrong answer if you round at different phases. Okay, so make sure that you're always carrying those numbers and you round at the end. And so if you're expected to report something in the middle, then you report per the sig figs, but you don't drop things when you do further calculations. Okay? And again, moles of PV, we're left with atoms of PV. So, and just atoms is fine, but that's what we're talking about. Okay? So now I can use those things that I have just learned, that the molar mass, 1 mole is the mass on the periodic table, and that mole contains 6.022 times 10 to the 23rd atoms or molecules. So I can go between the mass that I started with to the number of moles, from the number of moles to the number of atoms. So I can do that. It's perfectly possible and something I should be able to handle. So what's the difference between a molar mass and isotopic mass? We talked about this, remember? So we may not refer to them any different, okay? But if I know the number of electrons, protons, and neutrons, the mass is the sum of the protons and the neutrons, okay? And not the number on the periodic table. So if you've been told explicitly how many neutrons are given, or you have. So if you get one of these things that looks like 13, 9, F, then you know the number of neutrons equals 4. And so the mass equals 9 plus 4 equals 13, then that's what you report as the mass. So I may not say what's the isotopic mass, but I may ask for the mass, and I'm implying isotopic mass. Okay. So be careful. If you know how many neutrons there are, that's what we're looking for, not the number off the table. Okay. So that's why I mentioned that. Questions, comments, problems? Cool. Now, molecular mass, aka molecular weight. We use those terms interchangeably. Again, they are not. Weight is a mass under the force of gravity, so they are not the same thing. Now, molecular mass is the mass in AMU of one molecule. It's also the mass in grams of 1 mole. So the numbers that we look at on our periodic table, so for lead, it's 207.2 AMU for 1 molecule, or is 207.2 grams per mole. It's the sum of the atomic masses for the components in the molecule. So if we're not talking about an atom, then it's going to be everything within that molecule. So if I wanted to talk about H2O, we'd be looking at the mass for 2 hydrogens and 1 oxygen. If we wanted to talk about the mass of NaCl, it's the sum of the Na and the Cl. If we want to talk about NH2,2CO, this 2 that's here applies to the N, so there's 2 of those. And the hydrogen, there's 4 of those. And the CO, so 4 times the hydrogen, plus 2 times the nitrogen, plus the carbon, plus the oxygen. Okay, so make sure that we're distributing those numbers appropriately to make sure that we're calculating the mass correctly. Okay. So we have to make sure that we're accounting for everything that's in there. One of the biggest mistakes, and I'm guilty of it too, is I remember to distribute this 2 to the hydrogen, and I'll get 4 hydrogens. I don't always remember to do it to the nitrogen, and therefore my mass is not correct. So it's too small because I forgot to distribute it to that nitrogen. Okay, so that's how we calculate a molecular mass, is to accommodate all of the things that are in that molecule. Right. Questions on that? From here on out, we will expect that you can calculate a molecular mass and that you can use it to do what we're trying to do. So calculations using moles, mass, and numbers of atoms. This is really no different than what we've been talking about and what we did with lead, but now we're doing it for a molecule. So considering oxygen, Oxygen is one of those things that's diatomic, right? So it doesn't exist by itself, it's O2. I have a molar mass of 31.9988 because oxygen on this table is 15.999, right? Then 2 times that is 31.9988 grams per mole. How many moles of O2 do I have? I have a sample that's 267.84 grams. 267.84 grams of O2. I know that there are 31.9988 grams of O2 in 1 mole of O2. Grams cancel, and I'm left with moles of O2. Okay. That tells me when I set that up that I have 8.3703 moles of O2, which we can symbolize as MOL. Okay. And it's 5 sig figs that I report because this number, 1, 2, 3, 4, 5 sig figs. I report 8.3703. Even though 267.84 divided by 31.9988 would give me 8.370313887 of O2. So that's my unrounded number right here. I would then round this to 5 sig figs. Okay. All right. How many particles of O2 are there in the sample? And remember, we are continuing this calculation. And so we don't want to round that. And so we take this big, huge number right here, and then we multiply the number of moles by Avogadro's number. So we take the 8.3703138887 mole of O2. 6.022 times 10 to the 23rd molecules per mole. And that is equal to 5.04060302 8 times 10 to the 24 molecules of O2. Okay. Which is that lovely number that I've reported there. When I truncate that to 1, 2, 3, 4, 5, then I get the number that is reported. So 5.0406 sig figs. So I have the number of moles and atoms. Now notice what I've done here is I've done 2 separate calculations. So I did one to get to moles, and then I took that answer and I did another one to get to particles, molecules, atoms. Do I have to do it that way? Not really. So 267.84 grams of O2, 1 mole of O2, 31.9988 grams of O2. That would cancel my grams of O2 and I'd be in moles of O2. 1 mole of O2 contains 6.022 times 10 to the 23rd molecules of O2. Moles cancel. And then I can do this in one step to get to 5.006 10 4 molecules of O2. So I've done one calculation, rounded it appropriately for the sig figs that I have, and that is what I get. Can I do that? Absolutely, I can do that because then I don't have to think about what do I need to report at each step. I only have to report the number of sig figs that I should have one time. Okay. So I don't care how you do that. You can do it as one calculation or as multiple calculations. It's entirely up to you how you handle it. Okay. Questions, comments, problems on that? All right. I'm going to take a break here. I'm going to stop and get us a new video. So if anybody has any questions, please let me know.